For today's pre-lecture video, I chose two topics that I thought it might be better to cover outside of class and allow us more time for some other more important topics during class on Monday. So today we're going to look at two separate things. We're going to sort of see how we derive the idea of rotational and translational kinetic energy for a rolling object. And then we're also going to talk about work and torque, how they're calculated when we have rotation. So basically, when we have a body that's rotating about an axis, but the axis is moving, what we're going to find is the total kinetic energy is a total of translational kinetic energy and rotational kinetic energy. Now, we had a little problem with the translation of font here, so I want to just write that again. Total kinetic energy is a combination of translational kinetic energy and rotational kinetic energy, where the translational kinetic energy is due to the motion of the center of mass, and then the rotational kinetic energy is due to the rotation about the center of mass. And so what they're trying to show here is that when this baton is moving through the air, you see the dotted line, that's the motion of the center of mass, but you should also note that it's rotating about an axis through its center, and that's where the rotational kinetic energy comes in. Here we see how it's written or sort of demonstrated in a picture where we have the translation motion and the rotational motion. So the way that we're going to see how this falls out is we're going to imagine we have an object that's rotating about an axis. Here's the axis of rotation, and here's the rotational motion. And the object is moving. Here's the velocity of the center of mass, so it is moving as well as rotating. And so we're going to look at a single piece of it, little m sub I here, and we're going to talk about the kinetic energy of that little piece. The kinetic energy of that little piece is 1/2 m sub I times v sub I squared. So it's velocity squared. But we're going to write the velocity of that little piece in terms of the velocity of the center of mass. It's equal to the velocity of the center of mass plus the velocity relative to the center of mass. So we're just sort of thinking about different frames of reference. When we square that, v sub I squared is actually, when we square vectors, we haven't talked a lot about it, but what you're really doing is doing a dot product. So we would take the dot product of v sub m plus the velocity relative to the center of mass, and we're dotting that expression with itself. And what we're going to get is v sub m squared, velocity of the center of mass squared, because we'll get v sub m dotted with v sub m. And then sort of our FOIL method, we'll get 2 times v sub I prime dotted with v center of mass. Remember, the dot product is commutative, so it doesn't matter what the order is. And then finally, the velocity, sorry, it shouldn't have a vector on it, the velocity relative to the center of mass squared. Now, so the total kinetic energy we would find by summing all the kinetic energies up and then we could multiply that by this v squared term that we just found. And keep in mind that the sum of m sub I is just going to be the total mass of the object. So we're going to get a couple terms. One term is going to be 1/2 big M v sub m squared. Then we're going to get 1/2 times 2 times the sum of m sub I v sub I prime dot v sub m, and then plus 1/2 m sub I v sub I prime squared. So let's go to the next, because it's a lot here. So we had so we have to sort of remember some results that we had previously. So previously, when we saw that when we talked about the velocity relative to the center of mass, by definition, the sum of all the velocities relative to the center of mass, the sum of m sub I v sub I prime, is just 0. So this middle term is going to disappear. We're going to get 1/2 big M v sub m squared. And then this term, this is the velocity relative to the center of mass, which is actually going to talk about the rotational motion. And this would actually end up to be the 1/2 I c sub m omega squared. And so that's where we get that result. That the total kinetic energy of something, and this is when an object is not just rotating, but it's moving at the same time. We actually will want to talk about the translational motion as well as the rotational motion that the object has. So what we're going to do is we want to sort of see, well, how would we sort of deal with that in terms of energy? So we could look at a situation like this where we have a ball at the top of a ramp, and then we want to know how fast is it moving at the bottom of the ramp. So here we would use conservation of energy, and we have, want to think about what kind of potential and kinetic energy it has in both locations. At the top of the ramp, we'll assume that it's going to start from rest, so it only has potential energy equal to mgh, whatever the mass of the ball is. And then when it gets to the bottom, if we said that this was at the top of the ramp had a potential energy of mgh, then at the bottom of the ramp it doesn't have any potential energy, but it only has kinetic energy. But now instead of just writing 1/2 mv squared, we have to keep in mind that that's the translational motion, the fact that the axis that this ball is rolling about is moving. So that's the translational kinetic energy. And then we have to talk about the rotational kinetic energy for this object. And so those two terms have to be included when we're talking about kinetic energy. Now, let's say, suppose it's a sphere. Let's say it's solid. We might remember that the moment of inertia of a solid sphere is 2/5 mr squared. So we have mgh is equal to 1/2 mv squared plus 1/2, and then we put in the 2/5 mr squared. And then for omega squared, we can also use the fact that that's equal to v over r squared. And this is a way that we could sort of reduce this problem, because when we look at it here, we don't know the velocity or the angular velocity. But using this relationship here allows us to write everything in terms of the translational velocity, We also see that because we introduced the moment of inertia, now every term has a mass, and I can get rid of that. And that's something that should be interesting to you. So GH is equal to 1/2 v squared, and then this ends up to be plus 1/5 v squared. Notice the r's cancel out as well. And that's something that we want to talk about in class, because we did talk about how the moment of inertia of an object would affect how quickly it rolled down the incline. But notice that we also have no dependence on mass or the radius. So that means that no matter how large this sphere was, this ball was, whether it had a large radius like a bowling ball or a small radius like a marble, it would actually reach the same speed at the bottom of the incline regardless. And then for our second topic, I want to just go over quickly work when we're talking about rotational motion. Remember that for work, we have a force applied through a distance. So suppose this little girl is pushing the merry-go-round. She's applying a tangential force. Now, instead of the merry-go-round moving in the direction of the force, well, it will somewhat. It's going to undergo a displacement, ds. And so the work is still going to be F dot ds. But we're going to say that for a small displacement, these are going to be parallel to each other, so we can just write this as F ds. And then we can also remember that we wrote that S was equal to R theta, so ds can be written as R d theta. And then we can notice, oh hey, that would mean that quantity would be a torque. And so this allows us to write the work done by a force when it's going to cause a rotational motion. It can be calculated as the torque times integrated over theta. So we found work was equal to the integral of torque d theta. So we have that result. And so what if we want to think about energy and power? So remember that we got previously for translational motion, we had work equal to the change in the kinetic energy, 1/2 mv final squared minus 1/2 mv initial squared. It'd be interesting if we could find something similar for torque. And we're going to do exactly what we did when we found it for translational motion. We found earlier in this chapter that torque could be written as I alpha. And we know that alpha is d omega dt. But what if we want to write this? We're going to use the same sort of chain rule trick that we did when we did translational motion. And we, instead of writing this in terms of t, we could write it as d omega d theta dt, and then d theta. And so first, we have d omega d theta. D theta dt is just omega. And then we could also see that our d thetas are going to cancel out. So I get I omega d omega. And so this is actually then very similar to the integral that we had for translational motion, but it's just that I is replacing m and omega is replacing v. This is going to give us 1/2 I omega squared evaluated at the initial and final angular velocities. So work can be written as 1/2 I omega final squared minus 1/2 I omega initial squared equals the change in the kinetic rotational motion. So we found that there is a similar expression for work when we have rotational motion. We found that this can be equal to the change in rotational kinetic energy. So what about power? Remember that power is the rate at which work can be done. And so we could say, well, I know dW could be written as torque d theta. So work dt could be written as torque d theta dt could be written as torque omega. Remember that this looks a lot like in the previous chapter we found that it could be written as force times velocity. Notice that this is sort of the rotational equivalent. And so power could be written as torque times omega. And so we've kind of completed all the things that we wanted to cover. That will leave us a little bit more time to go into the other materials in Chapter 10 in more depth on Monday.